You just cried.
So,
You just cried.
the iron lab, right?
There is.
About that.
So you take the points from iron lab, put it on the ACS test.
Yes.
So, I mean, the issue is that you get this points, whatever. I mean, and I say that somewhat lightheartedly because, anyway, there's a whole educational philosophy side of the points thing that drives me bonkers. It's not, like, with respect to regular assessments, I've had like 0 questions about the points, which is awesome. Because ultimately it's not about points, it's whether you guys know and can do what you're supposed to know and can do at the end of it all. You know, and point accumulation is my very short soapbox on point accumulation is something entirely different than you demonstrating what you know to do. So anyway, the kind of the issue, I mean, this is a legitimate question though. You know, you collect that data from last week, which is, you know, absorbance, basically absorbance against time, because you don't know the concentration of the dye, and all you can do is measure how the absorbance changes over time. And you can graph the absorbance against time. You can take a natural loss, and you can invert this and that. I mean, you can build some graphs with it, but then the question is, you know, what do you do with that information? So, in all seriousness, not being snarky, but what do you do? If I had checked my email like 2 days earlier, I hadn't been on my email for a year, the other 2 instructors had canceled it. And I suspect it's because of this kind of question. You know, what do you do with it? The only reason it had double in Canvas is because last year we did a 2-part version of this one. I don't remember what the second part was. Remember, Amber, the second part?
We didn't do the second part.
Yeah, I think we did the first part, and then we didn't do the second. You know, and I suspect that, anyway, it got canceled by the other 2 instructors because of this question. I mean, you've got, that's it. So if you wrote it up, you know, outstanding, I'm not quite sure, to be honest, what kind of answer you're going to, you know, what you're trying to solve, show. I mean, seriously, if you did it, what did you do with it? So that's why, if you didn't do it because you're sitting there going, I don't know what to do with this data, then, you know, I'm good with that. If you did write it, and you turned it in, excellent.
Like reading material.
No extra. Kudos to you for doing something with this.
So, I can do it here and just so we're on the same page. I mean, that's...
If you haven't done it, don't turn it in.
You're a better student for it.
I'll look at
Better
it.
student than I.
What's that, right? Snarky comment?
So you're gonna look over them and figure out what the fuck you were supposed to do? See if anybody figured it out.
No, I actually don't. I don't like this lab a whole lot.
It was so wordy.
Yeah.
It was so hard to figure out.
It's not one that I would put in the manual, but that's not. I got the iron thiocyanate lab put in. I'd like to get this one pulled out and the other one put in. So, and given that they canceled, I think we canceled part 2 last year, and then they canceled, I think it's an easier push to make it go. Okay. Okay, you had your hand up, so. Or a stretch or something.
Me.
Okay.
Which is good for he says.
So there you go. Exactly.
We could prove it was first order, is what we could do.
Yeah, that's about it.
I mean,
Okay.
I mean, you can make the graph and look at the graphs,
It looks really pretty.
and there you go. And that's, but there's no,
You're gonna read over mine and be like, what?
but there's no question in the lab, like solve it, there's no post-lab questions, just you collect the data and that's it. I mean, and like I said, you can make some graphs, but there's nothing concrete to say, hey, figure this out. So, anyway.
so was it trying to say like, this is how long it takes to break down the pollutant, at the rate of breaking it down?
Yeah, but then which pollutant are you talking about? I mean, that's when
Just like staring.
when you talk about having these porous iron barriers that are sunk in the ground and polluted water flows through it, and there's this reaction. But
Yeah, and I guess like if you don't have any homework or anything left to do, you could probably crunch that out too.
And there's no like accepted or like.
yeah, in the lab you've got small pieces of iron and slightly larger pieces of iron, so you could have looked at how does the small chunk versus the big chunk differ. Does it differ? I mean, you got surface area, more surface area with smaller chunks, and you should see an increased rate of decomposition than you would with the bigger chunks, but it took long enough that I was not expecting y'all to go, oh, we're going to test the small ones, we're going to test the large ones, and then do it. Right? And some of you were shaking for a long time, you know. So, anyway, topic-wise, really, I can field questions that you all have. This goes all the way back to 161. I can put up sample questions, and I don't have any specific agenda other than, you got to know from 161 out. So try to go back to fall quarter and remember some of that stuff. Remember?
There was one thing that just kept popping up on all the ACS stuff I was looking at, and it's unit cell. I don't know what's going on for now because it's like a really big topic, I guess.
What was it?
No,
Unit cell?
Unit cells, they are,
XYZ.
yeah, they are horrible.
Like what? I don't. Yeah.
They are not things that, I don't know, I know they show up on occasion, but.
Long story short, we went over like 10 questions, just randomly. It was bad.
I think we missed all 10.
So, this is, I didn't cover this. I didn't cover this with you guys in 162 at all.
We talked about lattice energy, which I think is the same chapter.
So lattice energy is the energy required to separate a mole of an ionic solid and produce gaseous ions.
Right.
The unit cell has to do with how the atoms are packed inside of its crystal structure. And it's this stuff. And there's a lot of. So, in answer your question, I don't know if it's worth going through. The thing about unit cells is that you kind of have to have a real good three-dimensional ability on these things because you got to visualize how many that atom's connected to how many and in which way is it connected and how are they packed together. So if you have something like this one, I don't know if you can see that each one of these corners is 1/8 of a sphere.
Oh. So
Some of you will be able to look at this and say this particular unit cell that has 8 corners represents 1 atom. Because each of these corners has 1/8 of a sphere.
So that's why Y is 1.
Okay?
So my
That's a
Z is
simple.
3. Oh, that probably has to do with the
And then it
orbits.
gets into the questions you get into dealing with radii and whatnot have to do with how long the edge of the cell is and what you find on the edges of the cell versus the face of the cell. So like polonium, if they're contacted like this with the center, you can figure out the volume of this unit itself based on the radius of the sphere. And you're sitting there going, what?
It's more like, this is a lot.
It's a lot of spherical geometry inside of cubes.
Yeah, so on the ACS, the most common one I saw was
Think it blocks.
here's the cell, what's the formula in X, Y, and Z? What is the formula?
Because
As in, formula as in like,
Is it X2, Y, 3, Z, X,
'Cause-
whatever?
yeah, because like if you go back up to where you had it was
With the little dots.
that one?
further up. That one.
Yeah.
So it said for the one on the right, it said that it's like X, Y, and Z3, and that's what it refers to it as. Like it says, what is the formula? And then it has like all these weird options, and then it says X, Y, Z3 is the correct one. And Z is the outer corners, which makes sense because you were talking about how the outer corners are one atom.
Right.
But then I'm wondering why are the six atoms three? And then the center one is one, which makes sense. But then the only thing that doesn't make sense now does it have to do with orbitals or something?
No, it has to do like,
With how is it set
I'll
up?
be honest with you, I am not an expert on these things.
Okay, cool. Oh,
Yeah, that still looks like it's.
oh, so it's only, so half of the atom is sticking out, I guess? Half of each atom is sticking out? So when you add them together, it's only half of them?
It's just how it's packed.
Right, so they're actually
All
like
right,
on
so
the
here's your
outside
question,
of the
and-
cube.
Yep.
If you can visualize, this is going to be a visualization thing.
Yeah.
Okay, so the correct answer is right there. That one's in the middle. So there's your X, and there's one of those. Okay. The Y's are the little guys up here, and then they're at the corners. So there's 8 corners there, and each one of those corners is, go back here, and up to this thing, 1/8 of the sphere. So if you take, all 8 corners, at 1/8 of a sphere for each one, or 1/8 of an atom, in essence, you have one total Y in this unit cell. Okay, so this would be one in the middle. You got 1/8, 2/8, 3/8, 4/8, 5, 6, 7, 8 eighths, which means one
Right.
atom.
Yeah, that makes sense. 'Cause
All
the
right, so
Z's
there's
are
your
sticking
X, your
out.
Y, and then your Z's. You've got 6 faces, and the Z is on the face, which looks like face centered. It's this one right here where you've got a face centered. So this is red, right? Okay, so you've got 6 faces in each of these are the Z's. Each of the Z's, it's like you cut it in half, so you've got half a sphere on each face. So if you have 6 faces with half a sphere on each face, it gives you a total of 3.
Okay. So is it called a unit cell because it's like where you fit the least number of the minute or something?
Yeah.
Okay.
For that particular arrangement. Yeah.
Right. I'm
So,
sure there's many.
yeah, like this one you got 1x then. The Y's you got 8 of them, each one's 8. There's the 1Y. The Z's you got 1, 2, 3, 4, 5, 6 faces. Each Z is, like on this one, 1/2 on a face times 6 equals 3. The Y's are 1/8 times 8 corners equals 1. And then the X in the middle equals 1. So that's why. And something like this I mean, I suppose you could remember if an atom is located at the corners, then it's 1/8 of a sphere or 1/8 of an atom. If an atom is located on the face, then it's going to be 1/2, and if it's in the middle, that's going to be 1. So it's a body center.
I'm sure after 2 days.
Instead of a cube, like a hexagon or something crazy like that, and then you have to do some wild calculation to figure it out.
I don't think this one gets in there.
What is that?
Hexagonal positive.
Hexagonal closet.
Like, to make it more difficult is like ACS level difficult. Like,
What is
how
that?
would you
Like packing like this.
know what I find the X
Yeah. I'm just gonna say I wouldn't even bother with worrying about that. To be honest, I
Okay.
mean, trying to figure out this one
Too much time.
is, yeah. I mean, to be honest, most people, even going something like trying to figure out how many atoms are in something like a face-centered or a body-centered cubic. Most people struggle with that because of the three-dimensional nature of it. And so I wouldn't worry about the hexagons so much. Did you guys see any of the? Did you see any of these kinds of questions? For those of you who are working through the ACS stuff. Okay. So Marissa, here's the.
Oh.
Rhombohedral.
So the ones that the book gives you really are these ones right here. And then you've got all these other options,
I guess they all look.
like monoclinic, triclinic, there's a hexagonal, rhombohedron. So, I don't know, I wouldn't stress too much about the unit cells. I mean, A, B, C, D it, if you had one of those questions. So. Or you can take the time.
I was watching a video and they said always put C.
So then I wrote a test for one of my AP classes, and I made all the answers A except for one.
That's messed up.
You know, James, was it about 5 minutes and you saw people just like,
There was one person who got it. He's like, I see what he did. He marked them all A. He missed one because he just guessed. But I mean, something like that, you know, it messed up, but it's an exercise in asking students indirectly, are you comfortable and confident in your answers, regardless of what the choice is.
True.
Well,
Because you're
after I
making them
saw a
doubt
pattern
themselves.
like that, I feel like the teacher's messing with me, and then I really start second guessing.
Yeah, exactly.
Should be
Like, that's the
confident in your
point.
answers. So, I was just having a little fun.
Thank God you're not making this.
This might be a dumb question, but so on the random topics quiz 1,
Okay?
it says like which aqueous solution has the highest boiling point,
Yeah.
and so like I get in terms of like molality because of the number of like when things break apart, that's what you're concerned with, but what I had read something online that was talking about how with using like acids you want to look at the Ka value, and that it actually meant that H2SO4 should end up having more because more of it dissolves, whereas the H3PO4 wouldn't dissolve as completely, so it ends up not having as many. And I just wasn't sure if that was something that we might see.
I was trying to see if I have that question sitting here. So if you're looking at something like an acid versus an ionic compound that's soluble in water, the ionic compound is a little dissociated.
Right. But
and when you're looking at the acids, yeah, the Ka value comes into play. But if you have a low Ka value, then if there's a second dissociation, like for sulfuric acid, I don't know what the Kas are, or the Ka is the second one, but yeah, in answer to the question, H2SO4.
You're still zooming.
oh yeah, it's still zooming in.
I was picturing So there is that dissociation, and that was
Right.
you get 100% one. So you get two
Okay.
particles on that one, but the second dissociation,
So the H3PO4 may actually end up.
and the H3PO4, it's considered a weak acid to start. So even this dissociation is, I'd have to look at the Ka, but this will have a Ka less than 1. So even this dissociates not 100%. In terms of then the number of particles, comparing these two, you have definite 2 there plus whatever comes out of this one, and you can figure that out using the Ka. I mean, you can determine the percent association, and
So that should mean that the H2SO4 should have been right then, right?
Well, this one, wasn't the key to this one the hydrogen bonding? The association at all?
I gotta go look at. I have to look at the question.
I wrote it down.
Yeah, because I mean, it did. Well, it asked because it asked which one has the highest boiling point, but it gives it in molality. I could also like I have it up on my laptop. Like I was sharing with this audience because I looked up stuff with applicants and I was like, because I thought I didn't know the first time around. I was like, and so it was wrong. I was
Got
like,
it?
No, I didn't.
Did you? I have it on my laptop if you want to look at it.
Yeah, I just asked if I had it. Version. All right, so while I look at the Kas, as you're looking at that, then can you rule out any of the answers off just right up front? Why can you rule out that one? You're right. Why can you rule it out?
Second quiz. This is C6H1206.
So, here's the question: does that associate to give you any kind of
No.
multiple number of particles? No. Okay. That is 1 molar or 1 molality particles. Top one, acetic acid, is that.
What was the question? Highest boiling?
Yeah.
Highest
Which, like, the
association.
H3PO4 has more hydrogen bonding, but. Did you not get it right?
Yeah, I only did it one time.
Oh. Gotcha. Okay.
This one, that was just which ones I got wrong. So I was like, oh, I can go back through those.
Yeah.
Which ones I got wrong. This one. Except for
Right.
that happened wrong the first
Oh
time.
my god, I know. It was awful.
I just have a very large amount of homeworks to get through. And I was like,
Because I guess it's like tough because yes, it has significantly more particles, but it also has less hydrogen bonding. So I was kind of like, I don't know.
Wait, first, is the answer HCPO4?
Right.
Is this the Van Hall factor one?
Probably. I don't know the Van Hoff factor for these.
Because like when you estimate the Van Hall factor, you get whatever has higher.
You guys remember the Van Hoff factor?
Kind of.
Yeah, it was just an adjustment.
It's this thing, and the I, like, It's basically an
And it
adjustment.
says it has for H2O, not for 2H2O.
So in other words,
Oh.
yeah, that splits apart to give you H and then SL4, or H and HSL4, but then some of that will reassociate for a period of time, and then it dissociates and reassociates. Hydrogen bonding does come into play where some of the H's are going to they'll stick here. Okay. I don't know the Van Hoff factor for these two, and it might very well be, to be honest, if you plug in the Van Hoff factor, that you end up with a larger change based on that.
Okay.
You can't make the case that this is not split apart completely into two hydrogens and one sulfate. That's still a large number comparatively. Like that Ka2 is larger than phosphoric acid's Ka1. Fine.
So glucose has 4 hydroxyl groups on it, 4 OH bonds. So it'll form 4 hydrogen bonds, right? So it should be pretty difficult to boil that. I guess what I'm asking, why are we talking about dissociation at all? I don't get the connection.
The more particles you put in the way of the surface of water,
Yeah.
the more difficult it is to boil the water away.
Yeah.
Right? And so yes, there are 4 hydroxyl groups, plus you've got 2 COs. 4 or 5. So glucose looks something like that. You've got 5 hydroxyl groups plus these 2. So yes, you would see a change in the boiling point, but it's you get. I would describe it as interference. You get more interference with more particles in these 2 than you do with that one, because the molality number that you're looking at is the molality of particles, not the molality of the molecules. And when you're looking at something like if each of these red things is considered either the phosphoric or sulfuric or glucose, whatever, the more of those you put in there, the less, right? And glucose is considered one particle, even though it's got all the OHs on there and will hydrogen bond extensively. You still have only one, whereas with the others, like sulfuric acid, you have, if you look at both associations, you have at least 2 plus that third one, where there's a reasonable amount of association. With the H3PO4, you got potentially 4 particles instead of just the 1. So the more of these you put in the way, the greater the impact on the boiling point. And even when you're looking at something like, this is not the proper structure, but it works for our purposes. If you're looking at that thing, all of these are polar, so that entire unit will dipole bond to water. Same thing with phosphorus or phosphate. All of these are polar, so it will also dipole bond to water. So ultimately, you're looking at 2 things, and Amber, you're right. It may very well be that one right there.
That's why I'm seeing on a couple of cases, they look at the Van Hoff factor, like everything estimated by the amount of ions.
Right.
When you do the
So this one, even though there are 2 ions there, that Ka2 tells you that it's going to be less than 2. It's like 1.8 or something like that. And the Van Hoff, like I said, the Van Hoff factor is an estimate of the change in molality based on what happens with that thing as it dissociates and reforms. So that it's slightly less than, and like for sulfuric acid too, for the phosphoric acid, that adjustment factor is going to be slightly less than 3 because you don't have 4, because you don't have 4 particles entirely present. But I don't know those Van Hoff factors. And I don't even think, it's like, this particular book doesn't even talk about the Van Hoff factors.
Yeah, the way the ACS works is like, they want you to make assumptions for a lot of stuff, so one of these questions popped out, I assume they want you to estimate the Van Hoff.
Yeah.
That's what it ends up being.
So if you're estimating a Van Hoff factor, you got to think about, for instance, then I'll move on from this one. I don't want to. You won't see too many of these questions, so I don't want to spend a ton of time on it.
Okay.
But so it looked like that it dissociates to make 2 particles, but the I value is for sodium chloride. Side point. So it's slightly less, and then when you solve for the molality of the ions, it's like, if I say 1.0 molal, it's just a little bit less than 2 molal in ions. So this would dissociate to give you 2 ions per NaCl. But they will reform NaCl. It happens in solution, and that instantaneous sticking drops it from 2, meaning a 1 to 1 to 1, so 1 gives you 2, to something slightly less than that. And if you're trying to estimate it, this one's going to be slightly less than 2, this one's going to be slightly less than 4. Okay. So, looks like I selected the wrong button there. And you're looking at the Van Hoff factor, whatever happens to be. Okay. All right. So, I guess then other questions, do you want to look at any particular chapter? Do you want to? Okay, so empirical formula, very quickly under those. Those are moles, okay? And when you're solving for an empirical formula, you'll be given, I don't know if I can find the problem real fast, but you'll be given grams of whatever it is, and you get grams of whatever it is, and you need to convert that into moles and then moles, okay? And it'll let you write a formula, okay? So like in this case, it worked out to be X 0.1 and Y 0.2. If that's what it worked out to be mole-wise. Then the question is, what do you do with those decimals?
I'm sorry.
Okay.
Here you go, though. You can't drink the Vi coconut anymore.
Okay.
This is the best stuff.
It's $5 for 1 bottle. That's the best.
See ya. Okay. So then, pretty much all empirical formulas work the same way. There's one little tweak that sometimes shows up, but ultimately you're converting grams to moles. You get something like this. You got to deal with the decimals. A lot of people think, well, just multiply. The easiest thing to do, divide by the smallest of the numbers. That lets you get a formula that looks like that. That's empirical formulas. The couple tweaks on it that you'll see, sometimes you'll be given percentages like X% X and X% Y. if you see that, assume that you have 100 grams and it lets you give a straight percentage to grams conversion, which you can then take to moles, write this, and then solve. The only other thing that shows up sometimes is that you'll get, when you do this division, you get a number like a half. Sometimes you'll get thirds that show up. There's another odd one that shows up on occasion. You're looking for a multiplier. The question is then, what do you multiply halves by to turn them into whole numbers?
2.
2. So this one you x2, y3. What do you do with the third? 3. Multiply. So 3, x4, y3. Last one
7.
is a 7. Sometimes you get numbers that work out to be real close to whole numbers, so like x 1.02, y 2.99. Those you can round. That's close enough to round. Okay. The last thing you might see with empirical formulas, something like that's the empirical formula. This is the molecular formula. The question is, what goes in that box? Could you do that? Makes sense. Of course it can. what's the mass of that right there? So I should say this is a mass number.
30.
It's like 30 something.
So what's the multiplier?
4.
4. What's the formula?
C4H8O4.
Yeah. That's the other thing you see sometimes with empirical and molecular formulas, that you'll be given enough information like an empirical formula and the formula of the molecule, and then you're asked for that box. And it's a mass comparison. So if you can add up the masses here, multiply by 4, then you're good.
You get percentages stuff too.
Pardon?
Some percentages stuff too. Like this percent carbon, this percent oxygen, this percent.
Yeah, that's when you see the percentages.
Yeah.
Yeah, just assume that you got 100 grams, and that lets you go straight to from a percent to a gram. So if you had like 23% carbon, it's 23 grams of carbon. Okay. Empirical formula. Okay. Next. Mike?
I just had a question. So, jump around here, sorry about
Yeah,
that.
it's fine.
So when we're doing the whole electrochem thing, the E-cell for non-standard conditions, when we're using Q and all that, sometimes there's a problem where it didn't tell you which was oxidation, which was reduction. It just gave you reduction potentials for both.
Right.
So how do you figure out Q? Which one is top, which one's the bottom?
I'm guessing it's actually that. That should be the easiest one.
So in order to find Q, you've got to have
Oh, no, it's got a double.
the concentration,
That
right?
technically is one.
And
Right.
in answering the question, which one is the oxidation versus which one is the reduction,
D?
you're looking at this comparison. So if it's, and these are all listed as reduction potentials, the more positive it is, it's more likely to be reduction. Right. The more negative it is, the more likely it is to be oxidation. So comparing the two of them, that's like,
Oh, I had a 1 in 4 chance.
oh, I can't remember the example I had. The example I had was so something like this thing, and you're just given reduction potentials,
Yeah.
right? So then you keep that in mind, right? So oxidation and reduction.
Reduction.
And oxidation.
Right.
So then if you're writing it as part of an equation, the oxidation version of this one is going to be CD turning into CD2 plus, right? And then you have SN being reduced. And then you're probably given on a question like you're asking about, you're given concentration, so you have, I don't know, something like that.
Right, and then you have to figure out Q, so that one is cadmium over 10.
Yeah.
Okay. Is that anything, like, is it a, can you simplify it and say Q is like the anode half cell or the cathode half cell, or is there a way to go about that?
Yeah, I guess that's
Is that,
yeah, because that one right there, the cadmium is the oxidized, the tin is reduced, so that's anode and cathode. So you could look at it as anode or cathode.
and will that always be the
Yeah.
case? And same extension, but the reduction half cell, or I guess the cathode half cell, is that always where plating happens, if it's gonna happen?
Yeah. Yeah. And that's the I got a cell like this one right there. Whatever's in solution here, in this case copper, will plate onto the surface of that. And that's because your electrons flow from the anode all to the cathode. So the charge, negative charge builds up here. Ions come out of solution to absorb the electrons, I guess, for lack of a better term, or be reduced.
Right.
Okay. So the plating happens here. Anode's going to degrade over time. So this will dissolve and turn into zinc ions in solution. Okay. Other topic? Yeah, Dave.
So when if I'm looking at a practice test and they're asking about sigma bonds,
Okay.
are they gonna give us like? Do you think they'd give us a picture of it and we can just count them, or do we have to draw the whole thing?
Like, what is the problem? What does the question read?
It says how many sigma bonds are in a two I can't say it. Butane?
Two butane?
Yeah, two butane.
As in, like that?
Yeah.
Okay. And they don't even give you a picture of it, right?
No, they just say the formula.
And so that was going to be C4H8, right? Did they even give you this much?
It says CH3C, and then it has like the 3 lines for like the 3 bonds.
Oh, so they actually do this.
Yeah, and then CCH3.
So that's a 6. So they give you that much.
Yeah.
Okay. I got 2 responses. The first is that some of you might be able to, oh no, it's an 8. 1, 2, 3, 4. Some of you might be able to see this and count sigma bonds. My suggestion though, draw it out. And 6. And then counting sigma bonds and pi bonds becomes easier if you draw it out. Because number one, every single bond is a sigma bond. So if you just count the sigma bonds that are present, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Because every bond is a sigma bond. Okay. And then the pi bonds, a double bond is equal to 1 pi bond, a triple bond is equal to 2 pi bonds. So in this case, you've got 2 pi bonds. But like I say, some of you might be able, if you remember all this stuff real well, you might be able to look at this and say, I've got 3 bonds there and 1, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9 pi or sigma bonds, and then the double bond or triple bond gives me 2 more pi bonds. If not, draw it out, then count. And keep in mind that all bonds are sigma bonds, and then those 2 are your pi's. Okay, does that make sense? Okay. Other questions? All
Yeah, are you giving us a formula sheet, and if so, what might be on it?
I will probably, I'll have to remember to print these.
Please
But this is the one that, I don't have a problem with this particular sheet.
So
It's-
if we already have it printed, can we use it?
I suppose. As long as it's blindness is all that's on there.
Right.
So yeah. You've got some gas laws. Really, PV NRT is the one. The rest of them, on the gas laws, like, can you all see? Remember Charles' law and Boyle's law and Sachs' law? Remember? Do you remember all those from the gas laws? That should no. That should yes. Okay. So the first one is Boyle's law. It just tells you pressure and volume multiplied together, give you a constant number. The most common calculation with it is something like this: the pressure 1, volume 1 is pressure 2, volume 2. That when you multiply you take a gas under certain conditions and then manipulate those conditions. When you multiply the pressure and volume together in each case, they give you the same number. Okay, that's Boyle's law. You can say the same thing for Charles' law and Sachs' law. There's Avogadro's law, which is also known as Amundsen's law. Anyway, all of those are contained in the ideal gas law. So if I cover up those, I've got pressure times volume. If I get out the VNRT, I've got pressure on one side and then temperature on the other. I could rearrange this to get that one. If I cover up those 2, I've got the V and T on the opposite side of the equal sign, which could be rearranged to give you that. Okay. The point is, all the gas laws are in this. Okay. You could rearrange this to say pressure divided by temperature equals NR divided by V, and that would be a constant for that setup. You can rearrange it to say volume divided by temperature equals NR divided by P. That's going to be a constant for this. Okay. The other gas law that you might see is Dalton's. That if you've got, say, a bunch of gases like oxygen and carbon dioxide and argon in a container, that the total pressure inside the container is equal to the sum of the pressures of the gases. That one should be real intuitive. If you think about, like, you blow up a balloon, when you exhale, you're exhaling a bunch of gases. It's not just oxygen and just carbon dioxide. And then the balloon inside there, that pressure that's inside the balloon is made up of those gases that you exhale. All right, so there's those, and then let's see what else I have here. There's kinetics. Remember that one? Can be rewritten in y equals mx plus b format. You got a first order equation. This one's your second order half-life There's your equilibrium stuff, all of it. Some constants. So I'll try to remember to make copies of this. Okay. Other questions?
Do we have any formulas on there? Or do we-
Oh, I suppose. Yeah. Mole fractions? So mole fractions are it's like a percentage, but it's just written as like that. I mean, you're not multiplying by 100. So if you had a mixture of things and say it was 0.50 moles of whatever in 1.34, that's like 0 point something. Okay. Whatever that is. And there's no unit with it, it's just it is a number. That's it. That's mole. Okay. Any other concepts that you're buzzing on? David?
So the stability of a molecule is that dictated by when you do its different structures and whatever has the
What question? What's the question?
It says which is not a stable molecule. It gives us NF3, NF5, PF3, and PF5.
All right, good question on this one. For this particular question, you're being asked about expanding octets or not expanding octets. And you need to remember that elements in the second period no expanded octet, and that means nitrogen's only going to give you 3 bonds. And it doesn't matter what you connect it to, it's only going to give you 3 bonds. So this one would not happen. Phosphorus, so elements in the 3rd period and beyond, they can expand the octet, and they can do it in a number of ways. Phosphorus, for instance, if you write the dot notation, looks like that. And under certain conditions, you can expand those 5 electrons to give you an arrangement that looks like that. So with phosphorus, you've got 2 options. One, 3 bonds, that one works. Second one, that one, 5 bonds. That one works. Okay. A couple follow-up questions. Number 1. Could you give the shape around those?
Which one? Electron or molecular?
Molecular. Let's go molecular shape. Not the domain shape. Electron shape. Or molecular shape. So, how many electron domains around the phosphorus? 4. How many bonding domains?
3.
And 1 non-bonding is 1. Okay. So on a 4-domain arrangement with 3 bonding, 1 non-bonding, the shape is always going to be trigonal pyramid. Okay. If you were to draw that out, it looks like that. How about the shape around that one? Trigonal bipyramid. it looks like this. And I'm leaving out a bunch of electrons on the fluorines. And then in terms of the trigonal bipyramid part, there's the base of the pyramid, and then you've got one on top, you've got the second one down here on the bottom. So trigonal bipyramid. Next question on something like this. What can you say about the polarity of these two? Polar or non-polar? Okay. And you're looking at, in this case, how does the shape impact where the electronegativity or the polar bonds pull electrons. And in this case, fluorine's more electronegative than phosphorus. Phosphorus is 2.19, 3.98. So there's a pull on electrons away from the phosphorus. And it's generally, if I were to draw one big arrow, in that direction. So at least on my drawing down. For this one, polarity is equal and opposite. And if you think about vectors, if you know your vectors, there's no one direction that, like this, pulls down. This has got down, up, you've got sides. There's no one direction that has more of a pull than any other. Okay. So this one, non-polar, that one, polar. Okay. That one.
How can you tell which ones you have or just
For icebox questions, I guess I'd put it this way. If you can recognize it as an equilibrium and you've got some reaction, doesn't matter what it is. I would say you're never wrong if you make an icebox. You may not use it, but you're never wrong if you make one. That's the first thing I'd say. The second thing is, if you're given things like a K value, whether it's Ka, Kb, Kc, something like that, and you're asked for, like on an icebox, remember our initial change in equilibrium. If you're asked down here for some sort of an equilibrium concentration, then you want to use an icebox. Okay. And how you solve that's going to be based on, are you given initial concentrations? Are you given a change? Are you just given the Ka value and then a bunch of X's that you have to solve for? And there's a lot of different ways a question like this could be written. But bottom line is, if it's an equilibrium, I would say make an icebox. You may not need it. You may have the information where you don't need to solve for anything here, but it's a good way to organize the data that you use. That's not a like super specific, but it's a tough question to answer because there's so many ways you can look at it. But you're never wrong if you build the icebox. You just may not need it. All right, next, Jared.
Were you able to refresh us on the dispersion forces, the different strings?
Yeah, so you got, remember that every compound all compounds use London dispersion forces, and that's because these are based on simply electron movement. You know, like at a point in time, you can have more electrons located on one side of the compound than the other, and that creates an instantaneous dipole. So, whatever, carbon, carbon, carbon. For one reason, if you've got electrons there, that makes this side slightly negative, this side slightly positive. Okay. This is instantaneous dipole, meaning it happens for a moment in time, and then it disappears, because the electrons are always in motion. If there's another one of these nearby, that positive charge can attract electrons. So now you get an induced dipole in the next one. And that can continue through whatever, it's a gas or liquid, it doesn't matter. But it can continue through the entire what I'm going to call it. I mean, I want to say mixture, but it's not necessarily a mixture, but the entire liquid or solid. Okay. So everything uses London dispersion forces because of this, and they have electrons. It is weakest of them and that's because this can show up, and then it can just as quickly turn into, I'm off the screen, equal distribution like that, which means no partial positive, partial negative. The second one you've got is dipole, and this is where polar bonds show up. And two things here. Number one, just because it's got polar bonds doesn't mean that it's a polar molecule. So the question about shapes. So, I mean, this one, you've got polar bonds in both of them. This one's a polar molecule because of the shape. This one's a non-polar molecule because of the shape. This one will undergo dipole bonding. This one will not. Because the molecule itself is not polar. Okay. In terms of strength, so these are, I would put it this way. Constant dipoles, meaning they are polar because of the bonds that are in a molecule. All right, that make sense? Okay. And then the third one that you got to worry about is hydrogen bonding. And this is a unique dipole interaction, and it's present in things that have OHs. Mike's question earlier about colligative properties. If it's got NHs present or NHF. And that's because of the difference in polarity between those particular bonds. The OH bond is very polar, the NH bond is very polar, so is the HF. Okay. And that difference in electronegativity, the strength of that polarity, makes it so that the attraction between, say, this right here that attraction is very strong because this bond is so polar and these bonds are so polar. You could call this one, I don't know, medium strength in terms of intermolecular forces. This is going to be the strongest in terms of intermolecular forces. London dispersion forces are the weakest. If you're looking at something like, look at that one, gasoline.
What about ionic bonds?
So ionic bonds, finish this thought, I've got ionic bonds.
Yeah.
Something like the gasoline, this is hexane, it's in gasoline. This is entirely nonpolar, but it can be liquefied because of this concept, where you can create at an instant in time, one side that's partially positive, one side that's partially negative. That can make one hexane stick to the next, stick to the next, and then stick to the next. But it's really weak. That's why, like gasoline, you throw it on the ground on a hot day and it evaporates really fast. You put water on the ground on a hot day, it doesn't evaporate nearly as fast. They both will, but in terms of the speed of evaporation, that's because weaker intermolecular forces, stronger intermolecular forces. Okay. And then when you're looking at ionic bonding, in terms of I guess in terms of strength, there are a couple things. If you take this, Becca mentioned lattice energy earlier. If you take sodium chloride and say want to convert this into sodium ions in the gaseous state and chloride ions in the gaseous state, it takes a lot of energy to do that. That's the lattice energy. But in terms of dissolving, things that dissolve in water have the ability to be, I have a picture of this. They have the ability to be surrounded by the water molecule, and in doing so, become solvated. I'm trying to find a picture so that it's easier than me trying to draw it. But in something like sodium chloride, that sodium ion can get surrounded by water and fall away. And then the chloride can do the same thing, surrounded by water in that way. So it just automatically dissolves. When you're looking at something like, with respect to solubility, I don't know, something times 10 to the negative, whatever. But this one, it doesn't dissolve in water. The attraction between the sodium, the silver, and the chlorine is such that that process won't happen. Okay. You can still separate these into its gaseous ions by adding a bunch of energy to it. And I don't know what the lattice energy would be, but you could do that. But in terms of dissolving, this won't dissolve in water. The resulting increase in entropy is not enough to overcome the attraction between those two. So, okay. All right. Anything else? Mike?
Like the trends on ionization energies and
Yeah.
electron energies and stuff.
So, let's see what I brought. Let's see. On the periodic table, things like group 1 elements, they very easily lose their electrons, right? And they therefore have low ionization energies. If you've got this version of the table, one of the numbers back here is this red one, first ionization potential. I mean, you can look at the numbers, but generally speaking, these have lower ionization energies than things on the right. So you can look at it as left to right ionization energy increases. Top to bottom, the size of the atom has an impact. So when you're looking at something like hydrogen, which is really small, 1 electron, versus something like cesium, which has 5, 6 energy levels. So that outer shell electron is very far away. Easier to take that electron than it is from hydrogen. So ionization energies in that case decrease as you go down, but they increase left to right.
If you had to compare, like, one is one level higher, but one level left or right, how would you?
So like say sodium to calcium?
Yeah,
something like that.
Or even on the other side, you know, like we ran like
Sulfur and
like silicon and nitrogen, I think, or something like that.
So if you're comparing something like nitrogen to silicon, you can go with the assumption that metals are they more easily lose their electrons, and silicon's more metallic, so by extension, it'll lose its electrons easier, and I can't tell with that. I think that's an 8.
Directly?
Anyway, whatever, 8, and then 14. I think that's an 8. When you're looking at, and this one's an interesting one, if you look at nitrogen versus oxygen, the question is why is oxygen slightly less than nitrogen? If oxygen has 2 things happening, it's smaller and it's got more electrons and more protons. Why is oxygen slightly less?
You're asking.
I mean, that's a question that may show up. I might ask people. Any ideas on that one?
Because it forms the ion, the 2 ion.
So, the answer sits in this particular diagram. And it's kind of a tough one to see, but you've got 3 unpaired electrons all in different orbitals in space. That one is easier to take because it's paired, and taking it away leaves 3 single electrons all by themselves in 3-dimensional space, in different regions of space. So in doing so, you're removing the electron-electron repulsion that happens within an orbital by taking that one away. And that's why you get oxygens just a little less than nitrogen. So, yeah. So that would be ionization energy. When you're looking at things like atomic radius, it's good to know the general trend on radius, and that one is, it's also on the back here. But generally speaking, top to bottom, things get larger, left to right, things get smaller. Electronegativity trends, most electronegative, least electronegative. So as you go left to right, things get more electronegative. As you go top to bottom, things get less electronegative. Where the trends show. Yeah. Boiling points. You can look at that trend in the front, boiling point and melting point. Generally speaking, top to bottom. Things, their melting points and boiling points decrease. Cesium is, I can't read that number. 1 something. Anyway, you can hold cesium in your hand and it will melt. It melts it.
We're not going to have this periodic table, correct?
No, but the trends you should know. Like 301 kelvins is for the melting point. That's just above room temperature. But the trends. So you wouldn't have this. You wouldn't be expected to know the numbers, but knowing that like melting points decrease top to bottom, that's kind of the trend. Decrease top to bottom. On the left side. On the right side, because wait, there's more, right? It's all different. But on the right side, if you look at, like this table is good because the color tells you something about a state. The red ones are going to be gases, the blues are liquid, the black ones are solids. So in looking at melting points and boiling points, top to bottom on the right-hand side, just looking at these colors would tell you that as you go top to bottom, melting and boiling points increase. Just by looking at the color. Left side, you don't get that because everything is black, but you think about the size of the atom, larger atom, the attractions between them are weaker because there's further distance between the nuclei and their outer shells. So, yeah.
Electropositivity is just like a reversible electronegativity.
Was that on one of them?
Yeah, I saw a question like which one's electropositive. Now it seems to be that pump, like the reverse of.
Yeah. Okay. Angela, were there any other questions on here that you remember that gave you grief?
There's some biology stuff that, I don't know if that's very.
Ionization energy increases from the left side to the right side. Oh, like these two down here. Okay. Yeah, in trying to answer these ones, you'd probably have to Google them.
Are you telling us we
I can
should
explain them
Google
if you'd like, but These are some organic chemistry things, just kind of very
Why are they on the
quickly.
Gen Chem test?
This is,
But honestly, I'm just thinking it was the wrong exam that I printed.
no, this is one of these, some of the local exams like this one, they throw in some organic. I don't think the one that you have, I don't think so, I'd have to look, but I don't think it's got any organic on it. Like number 55, for instance, geometric isomerism is different arrangement in three-dimensional space, okay? And would you be able to draw all these? No, that's so geometric isomerism is asking the question, can you draw these things differently in three-dimensional space? The answer to this particular question is only on letter B. If you think about, for example, a double bond as a plane like that, and you examine the carbon chain, if I make these two carbons here up on top, it's the same thing but flipped over. I don't know if you can see that in space on paper, but if I invert that, they're coming out the bottom of the opposite side. It's the same thing. This one, these are like triple bonds are always linear, so you can't make this one look any different. B, and then I'll take Marissa's question. You can go into the bond and then out of the bond on opposite sides. This gets the name trans. And if you go into the bond and out of the bond on the same side of the bond, it gets the name cis. When you hear about things like trans fats in the twos, that's where a fat has a double bond present, and the carbons that make it up have this arrangement. That's a geometric isomer.
I don't really understand the difference between A and B. I feel like they're both just random.
So if let me do this. If I number the carbons 1, 2, 3, 4.
B is just the opposite of like the one that's right next to it. They just say the same thing with the A.
So here's my first question. Double bond wise, how are A and B different? I'm just going to give you a little these out. Just with respect to the double bond.
It's the same.
Think about the location. Are you just talking about these two or A and B?
Yeah, A and B.
These two? Or this one up here?
Yeah, the top one.
Okay, so on the first one, the double bonds between carbons 1 and 2, right? And on this one, the double bond is between carbons 2 and 3. So the location of the double bond is different. And because of that, when you make this drawing up here, I've got hydrogen, 3 hydrogens, and the chain can only go these drawings are the same. If I take this one here, like this, and I just turn it over, these two are the same. Okay. But for this one, since the double bond is between carbons number 2 and 3, the chain can go into and out of the double bonds in different ways. This one goes in and out on opposite sides of my red line. That's why it gets the name trans. This one goes into the bond and then out of the bond on the same side of my red line. That gets the name cis. So the difference is location. Okay. And since it's only on carbon number 1, these two are different. You can't make this any other way. There's only one way to draw this one. For letter B, because the double bond is on carbon 2, it lets you write 2 different arrangements. Those would be geometric isomers. Yeah, but I didn't talk about those in here. The other one, just for what it's worth, I'm not going to worry about number 58 or 50. 3627. Just in case an aromatic shows up. Aromatics have primarily 6 carbon rings with alternating double bonds. Okay. You find that this particular arrangement is in a lot of things that have very peculiar odors. Like, you know, you go to the store, you find almond flavoring in the little from the spice aisle. Almond flavoring is that 6 carbons with an extra C and O. That's almond flavoring, and it's an aromatic. Vanilla has this arrangement plus some other stuff. Okay, that's one of the reasons why you can think about them being aromatic. But it's this particular structure. This particular one's called naphthalene. It smells like urinal cakes. You know what urinal cakes smell like? Okay. And then this one over here on the right, there are aromatic 5 carbon chain or 5 carbon rings like this one. So you've got alternating double bonds. The 8 membered rings are not considered aromatic.
Does that one have double bonds in it?
It does. I had it.
That's 4.
Yeah, so even though they're alternating, the 8 membered rings are not considered aromatics. Alternating double bond 6 membered rings, yes. 5 membered ring, yeah. 7, yeah. 8s, no.
7's yes, 8's no.
Yeah.
For real.
Yeah.
Who wrote this test? For real.
I don't know.
I need their address.
And the number 60, you'd have to know the structure of DNA. And if you don't know the structure of DNA, then this becomes real difficult to answer.
Yeah, like 20%, 25% chance.
Yeah. That needs to be right.
Yeah.
But if you've had biology, you'd remember, I hope, that you got a sugar phosphate backbone. Anyway, there's oxygens involved. Phosphorus is connected to oxygens, not carbons and hydrogens. But again, you really would have to know the structure of DNA. Any others in here? Angelo, you need
36.
36, and then Jared. Remember that in answer to number 36, do you care about writing this thing?
Yeah.
Okay. So Henderson asked about, you can figure out the half neutralization point, which is, I don't know, somewhere back in here, that if you take pH pKa, it's somewhere right in this range. Find the neutralization point. I mean, you could eyeball it. It's somewhere, I don't know, somewhere about right there. So like 7.5, so then you're back at 3.75, somewhere here, which means that pH and pKa are somewhere right around 4.2. In order to figure out the molar mass, you'd have to, I'm going to say, I'm not even going to bother with that tonight, but you'd have to have some other information to calculate that particular number. And you can do it. One of the labs that I'd like to add actually does figure out the molar mass of an acid based on the titration, but it's more than I would want to do at the time as well. Okay. Any others? Jared?
Are we expected to have the solubility rules memorized at this point?
Okay, so on the solubility rules, I would say that, do you remember the first one?
Lithium, aluminum, something.
All nitrates are soluble. All nitrates, nitrites, acetates, chlorates are soluble. So if you remember that one, that's good. So that's the NO3, NO2, acetate. I think those are all of them that are in it. So all of those are soluble. Remember rule number 2. So essentially group 1 and ammonium salts are soluble. Sodium, potassium, lithium, etc. Okay. Whatever, doesn't matter. Sodium carbonate soluble, ammonium hydroxide soluble. All of the ammonium and then group 1 salts are going to be soluble. And then rule number 3, chlorides, bromides, iodides are soluble except there's one, silver.
Lead.
Lead. And? Mercury. Yeah. So I'd say 2 things. Number 1, if you remember those 3, that would take care of a lot of the solubility questions that you might see. The second thing is, if you see solubility questions and you're giving KSP, remember those KSP values will tell you about the solubility. I mean, if you look at any of these, like silver bromide, the KSP is going to be low. Lead, whatever, lead hydroxide, the KSP is going to be low. So you don't, I guess really you don't need to memorize the solubility rules because anything that deals with solubility, you should be given a KSP number, and that'll tell you something about the solubility. The closer it is to 1, the more soluble, the smaller, less than 1, the less soluble it is. But if you know numbers 1, 2, and 3, that'll take care of a lot of the solubility, just general net ionic questions, or general solubility about whatever that doesn't involve any kind of a KSP. Okay. Yeah?
You look at number 44.
44? Okay. So for arsenic, the first thing on, so 44 is right there. How many electrons in ground state in arsenic? Gas phase have quantum numbers N3 and L equals 1. Okay. If I write out, let's make this fit. Remember that N equals 1, L equals 0, and that's the S orbital. If N equals 2, L has 2 possibilities, S and L, or excuse me, 0 and 1, which is S and P. And then if you go to the N equals 3, you got L equals 0, which is the S orbital, 1, which is the P orbital, or 2, which is the D orbital set. Okay. If you didn't remember that, that's a real quick to do in your quantum numbers. And then the M sub L, which is the number of orbitals that are present, is positive L to negative L. So like for S orbitals, that's the only option. M sub L is equal to 0. This is going to have positive 1, 0, and negative 1, which gives you 3 different P orbitals. And then the D is positive 2, negative, or positive 2, positive 1, 0, 1, negative 1, negative 2 gives you 5. So for arsenic, this is a filling sequence. That's arsenic's electron configuration. And then in answer to the question, if you're looking for N equals 3, L equals 1, that's back to here, you're in. So the question is, in N equals 3, third energy level, and L equals 1, p orbitals, how many electrons are there? 6. If you're asked N equals 3, L equals 2, how many electrons are there? 10. Because L equals 2 is the d orbital set, there's 10. If N equals 4, L equals 0, there's 4, 0, 2. Is that? Yeah, but that question requires that you remember the possible values for your quantum numbers, and that's what you're looking at. If L is equal to 1, that's the p orbitals. Third energy level p has got 6 electrons. Alrighty. Anything else?
Back to the reduction potential thing. Does a higher or lower reduction potential mean anything as far as reactivity? Does a higher reduction potential mean it'll grow or not grow?
Yeah. Find my chart. It does. You can talk about the activity series of the metals with respect to their reduction potentials. So, lithium and sodium are among the most reactive metals. They've got the highest negative reduction potentials. Things like copper here, fairly non-reactive comparatively. So if you're talking about which is more reactive, lithium or copper, the larger negative is going to tell you that this is more easily oxidized than is copper.
So the less reduction potential, the more reactive it is.
Yeah, more negative. I put it more negative, but I mean less, yeah.
So then does reactivity always mean oxidation?
For the metals, yeah. Your metals are going to be oxidized. Iron rusts. The coating on copper pennies, that kind of brownish coating, it's copper oxide, which is an oxidation. Yeah, for them it is the oxidation. You throw lithium and sodium in water, you get flames and things can go boom. You throw copper in water, nothing happens. Okay. You're gonna be fine.
Easy for you to say.
I've accepted fate.
No, you're gonna be fine.
And do you know what you're gonna weigh it as?
Usually I on any kind of a final, I give it a double weight.
Okay.
So
8.
yeah, and I have to build a conversion for it, and then figure out how. I haven't done that yet. That's I've got until Monday night to do that. It's a long month road. I've got finals in my other school today, tomorrow, and Thursday. So, but those grades don't have to be until next year, so I've got time on this. But anyway, no, I'll have some sort of a conversion that will take the ACS score and then put it into a value of 8. So yeah, but it's not going to be a deal breaker. So that's why I'm saying you're going to be fine. It's not like.
So I know
You should do well and try to do your best, but it's not like that it's going to destroy you.
correct. I know on a lot of the tests, like let's say if we show our work, we use the correct methods or equations or whatnot, but we get the wrong answer, you can still give us like quite a bit of points for it. But there's no way to really show our work on that.
So
So is it a 0 or?
it's a Scantron. So you're gonna fill out, don't worry about Scantrons, I'll bring them, steal those from other school, I'll bring those in. But the methods of my madness on showing your work is that, I don't talk about this, but the reason people make mistakes is because they try to do shortcuts, they don't show work, and they invert things, anyway, 1,000 different mistakes that are made when people are not showing their work. So by forcing you to show your work, it forces you to do things the way you should. So when you come into a test like this, where you've got to solve things, if you're in this habit of showing your work, you can sit down with something like this, a piece of scratch paper or whatever, crank it out because you know how and what it's supposed to look like, and get the right answer. So I mean, there is a method to it. I don't just say show your work because I'm being an owner. I show your work because the end goal is that in doing so, you figure out, okay, now this is what solving an equilibrium problem should look like each time I solve an equilibrium problem. Or if I'm solving an electrochem, here's what it should look like each time.
Correct.
You're doing it properly. But if you're just doing it halfway and kind of somewhat putting numbers down that aren't correct, and then when I look at it, I can't say, hey, you inverted this or this goes here. So there's a method to it.
But at least you still gave points for the work that was being
Well,
shown.
realize that if you're doing the process correctly, I mean, you see me do silly math mistakes up here every now and then. I mean, those kinds of things happen, but if you're doing the process correctly, I mean, I can see, you know, like you make a mistake at this one point, but you can carry that mistake correctly through a series of problems. And this is a different test because you don't have those linked problems like I've been using.
Exactly.
But if you carry that mistake through and you do it correctly, and I can see that because you show your work, then, you know, I'm not going to say, if the end, see, this is where the end goal is you demonstrating that you can know and can do stuff versus point accumulation. If I'm just interested in point accumulation and the other problem is like 10 points or 6 points or whatever, and you get points from me, you know, you put this in and then you get 2 points and whatever, you know? But if you can correctly use the information, so you're showing me that you know what you're supposed to do and you can do it correctly, even if you take that one mistake and run it through the entire problem, doing it correctly with the incorrect number doesn't negate the fact that you're showing me you know what you're supposed to do.
Exactly.
So from an educational point of view, I'm getting rid of that point accumulation crap in favor of, you know, show me that you understand what you're supposed to do to solve a problem.
I want you to write the next ACS test. These idiots are really bad.
Yeah, I need a few more hours in my day.
Just in one day though, right?
Yeah, just in one day.
Do you write the test the night before?
I got a stash of questions, and most of the time it's sitting down and modifying it. You know, I know that in giving my test back that people make copies, and I know that copies are floating around out there. I don't know whether y'all, hey, you took 161 last year. Gotta take a look. So some of the questions may be the same. I modify them. But generally the only reason why I wait to put them together is that, I mean, if I don't get a topic covered completely, I want to make sure that that topic is not, I mean, it wouldn't be fair.
You did that a couple of times in 162. We would go over topics and we're like, it's fair game, right? And then we were like, yeah, sure. And then it's on that same test. Right?
Yeah, and then I tested the next week, so it's all good. And that's the other reason why, at least for me, multiple assessments lets me see progress. Whereas if it's just about point accumulation, you get two midterms and a final, and you're screwed. So again, the end goal is you got a body of knowledge and you know it. Which is different than a lot of instructors. Anyway, there's a little bit of education to watch.
So do you have an idea of kind of how many questions we should be aiming to get correct? I mean, of course, we'd like 100. I don't know that that's reasonable.
There are 70 questions.
Do you have it right there?
I do.
Where are you?
Wait,
where are you
bring
parked?
do
Oh, I know exactly what car he drives to.
I didn't drive the silver one today.
He's just trying to throw you off.
Bike license plate. Oh, okay.
I got 3 cars. I gotta buy a 4th car in September because my kid. All right.
Wait, you didn't answer my question.
What was your question?
It was how-
All of them, of course, but in all seriousness, kind of the way, like if I'm scaling it, the way I scale any kind of an AP test or whatever, if you can hit out of the, let's see, if you can hit 70%, so out of 70 is what, 49? If you can hit the 49 range, you're doing pretty well. But you guys have to understand that a test like this is written with the intent of being difficult. It's not written, it's a ceiling. I talked about ceiling versus floor tests. You do the state testing for schools, those are floor tests. This is a ceiling test. So it is intended to be difficult.
Yeah, because I know it said online it was something like if you get half of them right, then you're in like the then you're in the 50th percentile, but they give you 80% on it or something like that. It was weird.
For the AP test, which is, like I say, is this class, if you get half the multiple guess and half the free response, because they do 2 parts of the question, like a free response, write it out, question like, what did you see on my test? Anyway, you give 50% on both, then you get the pass. Which, I mean, doesn't seem like a lot, but that's the way they consider it. If you hit that, it depends on your, it floats right around 68 to 70% overall. If you hit the 68 to 70%, that's considered a 5, which would be an A or a 4. So it is intended to be a difficult test. So when you come in here, do your best. Think about it, cry, eliminate answers and whatnot, but,
Did you just say cry?
no, cross out.
Oh, they'll be fine.
Anyway, I you can hit into the 40s and up and super well. So,
I just
might miss some. I don't know.